Welcome to the deep dive. Today we're peeling back the layers on something really vital for our modern grids. Grid forming, or GFM, inverters.
Right.
These are the components often working behind the scenes, playing a crucial role in getting more renewable energy online reliably. So our deep dive today is all about understanding how these, cutting-edge devices handle electrical disturbances and keep the power system stable.
And it's a really significant engineering challenge,
Yeah.
because these GFM inverters are just fundamentally different from the traditional synchronous generators we've relied on for, over a century.
How so? Exactly.
Well, think about overcurrents. Your classic synchronous generator, it can handle huge surges, maybe 5, even 7 times its normal operating current. Massive headroom.
Okay.
But GFM inverters, because they rely on power semiconductors, they're much more sensitive. They're typically limited to about, say, 1.2 to maybe 2 times their normal current. That's it.
Wow. Okay, that's a huge difference.
It really is.
Yeah.
And that difference is precisely why their current limiting controls aren't just some optional extra feature. No, they're absolutely essential, both for protecting the inverter itself and, just as importantly, for supporting the stability of the whole grid during a fault.
That inherent limitation definitely changes the game then. So, what does this mean for how these GFM control systems actually need to work? What are their core jobs?
Yeah, good question. Our sources basically boil it down to 3 core requirements. First, pretty obviously current magnitude limitation. You've got to protect the hardware.
Makes sense.
Second, fault current contribution. The inverter can't just protect itself. It needs to actually help the grid during a problem, like injecting reactive current quickly to prop up voltage.
Right. Be a team player.
Exactly. And finally, fault recovery capability. Once the disturbance is gone, it needs to get back to normal operation, fast, smoothly.
Protect, contribute, recover.
Got it. So with those requirements in mind, the research seems to point towards 3 main approaches or categories for these current limiting controls. Current limiters, virtual impedance, and voltage limiters.
That's right. Those are the big 3 families of methods.
Okay, let's dig into the first one. Current limiters. How do they work?
So, current limiters, they work pretty much as the name suggests. They directly restrict the output current. Often, this makes the inverter behave more like a current source during the fault.
Okay, so it caps the current directly. Sounds effective.
It is effective at controlling the magnitude of the current, yes. But there's a significant downside, something called wind-up in the voltage controllers.
Wind up.
Yeah, think of it like, imagine the controller trying to maintain voltage, but the current limit is preventing it. The controller keeps demanding more action, building up this internal error signal. It winds up.
Ah, I see. And when the fault clears, that wound-up controller takes time to unwind, which really hinders a smooth, fast recovery back to normal operation. Some types can even distort the output, creating non-sinusoidal currents, which is definitely not ideal for the grid.
Okay, so effective limiting, but potential recovery problems. What about the next category, virtual impedance?
Right, virtual impedance methods take a different approach. Instead of directly capping the current, they virtually increase the inverter's output impedance through control loops.
So it acts like it has higher impedance.
Exactly. The goal here is to maintain the inverter's desirable behavior as a voltage source, even during the fault. That voltage source behavior is really helpful because it lets the inverter naturally support the grid voltage, similar to how a traditional generator does. This generally aids in automatic fault recovery.
That sounds promising. Any drawbacks?
Well, yes. The simulations discussed in the sources show they aren't perfect limiters. You can still get temporary overcurrents peaks up to maybe 1.5 times the nominal current we're seeing. And it involves a pretty delicate tuning exercise, balancing the current limitation against maintaining overall system stability. It's a tricky trade-off.
Okay, still a balancing act. So that brings us to the third type, voltage limiters. How do they fit in, especially compared to virtual impedance on those overcurrents?
Voltage limiters, they work by directly reducing the inverter's internal voltage reference during a fault. Like virtual impedance, the goal is also to preserve that voltage source characteristic. So they're generally good for automatic fault recovery too.
But I sense a but coming.
You sense correctly. Here's a really critical finding from the simulations, these voltage limiter methods. They can actually generate the largest temporary overcurrents of the 3 types.
Really? How large?
We're talking peaks hitting twice the normal current, maybe even a bit more, and lasting for a significant duration, like 20 to 25 milliseconds.
Whoa. Why is that?
It seems to be largely down to a lack of inherent damping in how they operate. When the voltage is suddenly reduced or restored, There isn't a strong internal mechanism to quickly suppress the resulting current oscillations. So you maintain that voltage source behavior, which is good, but potentially at the cost of seriously stressing the inverter's components during those peaks.
It really sounds like each method is trying to juggle those three core requirements: protect, contribute, recover, but they all bump up against different limitations. No silver bullet, huh?
Not yet, it seems. And this really highlights some of the major open questions in the field.
Right. What are the biggest challenges researchers are still grappling with?
Well, two things really stand out. First, that persistent problem of voltage controller windup, particularly with current limiter methods, but it can be a factor elsewhere too. Finding ways to prevent that windup or manage it better is key for seamless fault recovery.
Okay, that makes sense. And the second?
The second big challenge is designing controls that can reliably maintain that desired voltage source behavior, especially under overcurrent conditions, while also guaranteeing transient stability. It's easy to be stable in normal operation. It's much harder during and right after a fault.
And why is maintaining that voltage source behavior under stress so critical?
Because that's what allows the inverter to provide really fast grid support. Think about grid codes. They increasingly demand things like reactive current injection within milliseconds of a voltage dip. Only something behaving like a stiff voltage source can really respond that quickly and effectively. It's vital for keeping the modern grid stable with lots of renewables.
It's truly amazing the level of sophisticated engineering required just to integrate clean energy sources reliably. This deep dive really underscores how intricate that balancing act is.
Absolutely. It's a constant push and pull between different objectives.
So next time you think about clean energy powering your home or your city, maybe take a moment to consider this complex dance, this interplay of protection, contribution, and recovery that these GFM inverters are performing constantly, balancing all these demands just to keep our modern grids stable and running smoothly.